This last section we're taking a look at, section 11.10. I'm splitting this into two parts, but we're going to look at something called the Taylor and Maclaurin series. So we're going to start with the theorem. If our function f has a power series representation, at x equals a, say for example f of x is equal to the sum as n goes from 0 to infinity of c sub n times the quantity x minus a to the nth power, where the absolute value of x minus a is less than r, then the coefficient is given by, we'll say c sub n is going to equal the nth derivative, so we're going to write it like this, the nth derivative at x equals a over n factorial. So that's our coefficient. So again, just to make a note, this notation here means it is the nth derivative of f of x. So our function can be written as the series, the summation as n goes from 0 to infinity. Instead of c sub n, we would have the nth derivative at x equals a over n factorial times x minus a to the nth, which is really equal to, if n is 0, we would just get our function f of a, so this would be f of a, because this is 0 factorial, which is actually equal to 1, and then this would become something to the 0 power, which is 1. Then we would have f prime, the first derivative of f of a, over 1 factorial times the quantity x minus a to the first, plus the second derivative now of f of a over 2 factorial times the quantity x minus a squared, and so on. So this is called a Taylor series. And we call it either a Taylor series of the function f at x equals a, or a Taylor series centered at x equals a. Now for a special case where x, or rather a, is equal to 0, we have the following. The sum as n goes from 0 to infinity of the nth derivative of f at 0 over n factorial times x. And so if it's x minus a and a is 0, we just get x to the nth power, which is equal to, we would just have our function, because it will be just f to the 0, so it's just going to be no derivative, just our function, f of 0, plus our first derivative of f of 0 over 1 factorial times x, plus our second derivative of f of 0 over 2 factorial times x squared, and so on. So this is called the Maclaurin series. And that's what we're going to focus on in this first part. In the second part, I'll do a little bit more with Taylor series. All right, so for our first example, let's find the Maclaurin series for this function f of x, which is equal to e to the x. So what we first focus on is our function, which is f of x is equal to e to the x. And then we start taking a series of derivatives. So the first derivative, and this is nice because the derivative of e to the x is e to the x. Our second derivative is still e to the x. Our third derivative, still e to the x. So no matter how many times we find this, so the nth derivative of f of x would still be e to the x. So since this is a Maclaurin series, we evaluate this at x equals 0. Because again, a is 0 and we're centered at a, so it's the same thing as saying x equals 0. All right, so first what I want to do is figure out, well, what is f of 0? So I go back up here, and that's just e to the 0, which is 1. Our first derivative, since these are all e to the x, is still going to be 1, all the way down to our nth derivative at x equals 0 is going to be 1. So now we say the sum as n goes from 0 to infinity of the nth derivative of f of 0 over n factorial times x to the n becomes, since all of these are 1, I don't actually have to write out every term, so this will just become a 1. So now I get the sum as n goes from 0 to infinity. This will just be 1 over n factorial times x to the n, so I just get x to the n over n factorial. Now, if we were to use the ratio test, the limit here would be 0 for all real values of x, so we would say the radius, that was something that we did back in 11.8, we would say the radius of convergence is infinity. And again, because if we were to use the ratio test, the limit as n approaches 0 of that ratio would be 0 for all real values of x. Right, let's try another example. Again, let's find the Maclaurin series for f of x is equal to cosine x. So let's start f of x is equal to cosine x. Our first derivative, that would be negative sine x. Our second derivative, now we would have negative cosine x. Our third derivative would be positive sine x, because we already have the negative here, and the derivative of cosine x is negative sine x, so the two negatives become positive. This is how we would write the fourth derivative of f of x. We have cosine x. Now we're kind of back at the beginning, but I want to write this out a few more times. The fifth derivative, negative sine x. The sixth derivative would become a negative cosine x, and so on. So again, since this is Maclaurin, we evaluate all of these derivatives over here at x equals 0. So we would have f of 0, cosine of 0 is 1. The first derivative at x equals 0, so sine of 0 is 0, so we would get 0. So unlike the last example, these are now different. So our second derivative, we're now at negative cosine of 0, so that's a negative 1. Third derivative, sine of 0 is 0. Fourth derivative, cosine of 0 is 1. Fifth derivative, we'd be back at a 0. Sixth derivative, we would be at a negative 1, and so on. So then we would write this now. We would say, so cosine of x is now equal to the sum as n goes from 0 to infinity of the nth derivative of f of 0 over n factorial times x to the nth power. Well, because these are all different, I need to write these out. So we're going to get, when n is 0, we're looking right up here, we're going to have a 1, so this numerator becomes a 1. 1 factorial, because, I'm sorry, 0 factorial is 1, so we get a 1 over 1 times x to the 0, so that whole first term is a 1. Our next term, our numerator is going to become a 0, so that makes the whole thing 0, so we get 1 plus 0 when n is equal to 1. When n is equal to 2, we're taking our second derivative, so this numerator is a negative 1, so we'll have a minus. And then we'll have, so pretty much negative 1 over 2 factorial times x squared. So we'll get a minus x squared over 2 factorial. The next one we're going to have a plus 0, so we're at the third. Then we'll have, when n is 4, we're at a positive 1, so we'll say plus. Then we'll just have 1 over 4 factorial times x to the 4th. So we have x to the 4th over 4 factorial. To the 5th here, when n is 5, we'll get a 0. Then we're back at a minus here. So when n is 6, our 6th derivative, we'll just get x to the 6th over 6 factorial, and so on. So this really becomes, it's an alternating series. If we were to just write this out without the zeros, we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So this really becomes the series as n goes from 0 to infinity. It's alternating, so I'm going to need a negative 1. And since my first term is positive, we could just put an n there. Now, if you look at these numerators, they're all x to an even power, so we'll say x to the 2n, and all of the denominators are even power, or even values with the factorial, so we'll just say 2n and then factorial. And again, if we were to conduct the ratio test, the limit as n approaches infinity here would give us 0, so the radius of convergence is infinity. Now it's nice because we found this, we can use it to help us with our next example. So let's find the Maclaurin series for f of x is equal to sine x. Well, rather than going through all the derivatives and then having to write something out as a series and then condense it, we can use the fact that the derivative of cosine x is equal to negative sine x, which gets us pretty close to this. So we're going to do this a little bit smarter now. So if we were to take the derivative of cosine x dx, that means we're going to take the derivative of that summation that we just found. Negative 1 to the n times x to the 2n over 2n factorial. So here we're going to get a negative sine x. Now remember, when we take the derivative, our first term goes away, or we lose it. So now we're going, the sum, go back to section 11.9 on this, the sum as n goes from 1 to infinity. So we're going to take the derivative of this, so now this just becomes, again, this negative 1 to the n, and then 2n factorial, that's just a constant, so that's all going to stay there. Think of that as like our coefficient. And then we'll take really just the power rule here, so we'll get a 2n times x to the 2n minus 1. Now I'm going to do a little bit of algebraic simplifying here. So I'm looking at this 2n and then 2n factorial. So this will become 2n, and then 2n factorial will be the same as 2n times 2n minus 1 times 2n minus 2. So we'll put a factorial here. So this just becomes 1 over 2n minus 1 factorial. So now I get negative sine x is equal to the summation as n goes from 1 to infinity of negative 1 to the nth power times x to the 2n minus 1 over 2n minus 1 factorial. Now we'll divide both sides by a negative 1, so this is going to switch some things for us. So right now, this would be negative. So if I divide that by a negative, it's now going to become positive. So I'm going to say n goes from 1 to infinity still. So I'm going to have negative 1, and I need this to be positive, so I'm just going to do an n plus 1, because now that'll give me a negative 1 squared, which will give me a positive 1, and everything else still stays the same. Or if you think about it, what we did is if I divided or multiply, let's say I multiply both sides by a negative 1. So if I had negative 1 times the negative 1 to the nth power that was already there, I add the exponent. So I get negative 1 to the n plus 1. Now one more thing to do here, because we always want to bring it back to 0. So we're going to say sine x is going to be the summation as n goes from 0 to infinity. So I still want everything to work out nicely here. So now, if n is 0 and I want this first term to still be positive, I could simply bring this back to negative 1 to the nth power. Now if n is 1, this gives me 2 times 1, so 2 minus 1 is 1, so I still need this to give me a 1, so we're going to say 2n, because that's 2 times 0, plus 1. So this will still give me a 1 here. That should be a factorial. And then the same thing here. If n is 1, this will give me a 1. So when n is 0, I still need this to give me a 1, so this will turn this into a 2n plus 1 factorial. So we just have to shift things around a little bit so that we're still getting the same values. If we were to plug 1 in here, I still need the same thing when I go to plug 0 in. So that is the Maclaurin series for sine f of x is equal to sine x. So let's kind of summarize what we have so far. I'm going to add I think one more to this, but I want you guys just to memorize these. So kind of commit this to memory. So we have 1 over 1 minus x becomes the series sum as n goes from 0 to infinity of x to the nth power. This is valid for the absolute value of all x's here less than 1. We have e to the x. We have the summation as n goes from 0 to infinity of x to the nth power over n factorial. Valid, again, this is a symbol for all x. We have sine x is equal to the sum as n goes from 0 to infinity of negative 1 to the nth power, x to the 2n plus 1 over 2n plus 1 factorial. And if you recall, y equals sine of x is an odd function. And if you look here, 2n plus 1, these would give us all odd terms. And then cosine x becomes the sum as n goes from 0 to infinity of negative 1 times x to the 2n over 2n factorial. Y equals cosine x is an even function, so notice 2n is even. Then I'll add one more here. We didn't do this as an example, but if we were to, this is what it would come out to be. Inverse tangent x or arctangent x is equal to the sum as n goes from 0 to infinity, negative 1 to the nth power, x to the 2n plus 1 over 2n plus 1. So it's very close to sine x, just there's no factorial in the denominator. So again, going back to the sine x, this is valid for all x. So is cosine valid for all x. Now this one, the arctangent, because it is an inverse trig function, it is valid for all x values from negative 1 to 1.